Hey, hello everyone. I'm Bomee Lee, a postdoc at Caltech IPAC. It's a great pleasure to see our CANDELS people again. I'm so sorry I cannot meet in person though. Today I present my research working with, Dr. Rangaram Chari here at IPAC, which are mostly done with HST CANDELS data for future wide area surveys. First, I will briefly explain weak gravitational lensing. Second, I will introduce new galaxy templates that populates 3-color space and is constrained by HST CANDELS photometry. Then I will conclude with our recently accepted HST archive legacy project with gravitational lensing in the NIR IR with CANDELS and Cosmos Dash. I think you probably heard that mass bends light. So the gravitational lensing is a deflection of light by all gravitational mass. When light from distant galaxies travel through the gravitational field of intervening large-scale structure, light is slightly deflected and background images get weakly distorted and produce single images of sources. This is weak gravitational lensing. So you can think most of galaxies in the universe are slightly distorted by weak gravitational lensing. So the weak lensing is a powerful cosmological proof of distribution of dark matters, but the effect is very, very weak. So galaxies are not intrinsically circular and they are actually randomly oriented. So when the light from a group of galaxies here passes through the universe, the galaxy images show a slight alignment along a particular direction by weak lensing. This common alignment of galaxies is called cosmic shear. So to measure this common alignment, we need to measure the ellipticities of individual galaxies, then statistically estimate this alignment by averaging over ellipticities of galaxies in this group or small patch of skies. So the weak lensing observations require a large survey with high quality images to have large number density of reserved galaxies for sufficiently unbiased estimates of galaxy shapes. So by quantifying the amplitude of the weak lensing distortion, which is actually cosmic shear, we can directly map the distribution of matter. This is the 2-dimensional dark matter map of dark energy survey collaboration. Different colors represent density of matters. Redder colors represent denser regions, and while the bluer colors are less dense regions. So the background galaxies in these redder regions are distorted more by weak lensing than galaxies in the bluer region. We can also construct a 3-dimensional map sliced by redshifts through the universe that will show how the distribution of matter has changed over time, which depends on dark energy. So weak lensing is one of the main science goals of the future wide area surveys with Rubin, Euclid, and Roman. To map 3-dimensional weak lensing map, we need photometry redshift estimates. The photo Z precision requirement of those surveys is stringent. However, those surveys have limited number of bands. So in this galaxy SEDs, green circles, green points here are the Rubin LSST bands, UGRIGY bands. And the orange points here are the Euclid near IR band, YJH band. And the blue circles are the Roman GYJH plus F184 bands. So for this galaxy at redshift 2.3, 4,000 Armstrong Balmer break is located between J and H band, which can be obtained from Euclid or Roman. Only with LSST band, the redshift estimate might go wrong, especially at redshift greater than 2. Also, Euclid and Roman should rely on deep singing limited ground-based optical bands from LSST or other ground-based surveys. So however, still for future large surveys, 8 to 9 bands are the maximum to use, as you can see. So we introduced a new library of galaxy SED templates constrained with observed colors to improve the photo G estimation of galaxies having small number of photometric bands. For our purpose, HS CANDELS is the optimal data set to train Galaxy SED templates, as it has excellent spectral coverage and unprecedented depth and the spatial resolution, as all you know. Here, this is the HST I-band images, ACS F606W, with isopods, blue isopods here, derived from photometry comparing to other surveys having worse spatial resolution and smaller depth. The red is Euclid optical band, and the green is LSST 10 years. The green isopod is from the LSST 10 years. And this is LSST single digit. So you can see the source in the seeing limited images here can bias photometry because of the blending of the sources. So by using the CANDELS catalog, we have the highest quality photometry available to build up the spectral energy distribution of the training sample of galaxies. In this work, for the training sample, instead of the usual training set with the spectroscopic redshift, we use about 40,000 galaxies with CANDELS photometry redshift. By doing so, we build a large training set that has the best quality photometry and that are not biased toward strong emission line sources like spectral sources. Our method is quite simple. Step 1, we choose V-H, I-J, and G-H colors after experimenting with various combinations of color space. Using those V-H, I-J, and G-H colors, we simply make bins in each color space with a bin size of 0.2 magnitude to build color cubes in 3-dimensional color space. Step 2, we obtain the best peak spectral energy distribution of each galaxy in the training sample as fixing redshift to CANDELS photo-G. Step 3, we construct a color cube-based template library using best-fit SEDs shifted to rest frame wavelengths. The best-fit SED of each galaxy in the training sample is assigned to its designated color cubes. Here you are seeing 3 color cubes and 3 sets of galaxy SEDs here. Those color cubes are located differently in V-H, I-J, and G-H space. Purple, red, and green boxes have different types of galaxy SEDs, as you can see. However, if the cubes are located closely, their SEDs are very similar, like green and orange cubes here. So step 4, now we can derive the photo-G of galaxies using our new library of SED templates per color cubes. If a target galaxy is located in the purple cube here, the photo-G of this galaxy is derived by only using those 23 templates here. Okay. So to test our method, we derive photo-G of galaxies using our new library of galaxy SEDs with 8 bands, U, B, V, I, G, Y, J of galaxies in good, south, and north, which are comparable to LSST+Euclid-deep Roman-like photometry. So as a result, we obtain a photo-G precision, the sigma NMAD, of 0.026 to 0.028, and the outlier fraction of about 6% at redshift less than 5. We compare our results with the photo-Gs obtained with easy library using a wide range of templates for each galaxy. So here, this is a plot of sigma NMAD and the outlier fraction as a function of spectroscopic redshift of our target galaxies. Blue point is this work, and the orange point is result from easy library. So outlier fraction is similar or slightly better with our method. And we find that our new template library is very effective at redshift greater than 2 with significantly small sigma NMAD of 0.04 comparing to easy is 0.06. Especially at redshift between 2 and 3, sigma NMAD is improved by about 30% with our library. So there are 2 main advantages in our method. First, having a photo-G training sample allows the SEDs of dusty galaxies to be constrained and distinguished from highly Lyman break galaxies. So actually having a purely spectral training sample would make it challenging to constrain the SEDs of dusty galaxies because spectral samples tend to be biased against dusty galaxies. So we can determine the best fit better for large dusty galaxies, which would be fitted to be high galaxies otherwise. Second, we constrain the range of templates applicable to a galaxy to each galaxy using 3-color space with a photology training sample. So we are constraining the range of extinction values that may be possible among high-res galaxies. We are also constraining the range of star formation history in each redshift beam, which helps reduce color redshift degeneracies and the scatter at high redshift. So in conclusion, our color cube-based template library clearly has a merit, especially for future large extragalactic surveys, which will provide deep UGRIG YJH photometry. Okay, so I'll move to the next section. Do you have any question about our photology work?
So this is really cool, and I'm going to wait for a bit. If people don't have questions, then I have a couple.
Okay.
Okay. So if people have questions, please feel free to ask them or type them in the chat, whatever is convenient. And so I find this really cool.
Mm-hmm.
And in some senses, the color selection that you're doing reminds me of work by people like Dan Masters, Peter Kapak, and Shubi, where they try to compress things into a self-organized map.
Yes, yes, yes.
And then like assign a redshift based on which cell in the SOM a galaxy's SED would fall into.
Yes, it can be similar. They use the machine learning for the they actually find like a clustering of the observed colors, right?
Mm-hmm.
Using the SOM. But our method is actually we don't use machine learning because the one reason is that we cannot track all information from the machine learning by ourselves. We cannot see why this is happening, why this is clustered in this region, color region, something like that. So we decide to just bind with a 0.2 magnitude, which is actually about 5 sigma scalar in magnitude of the galaxies, right? So I think we can think more physically by doing that, but it's for sure you can do similar things with machine learning for sure. But I'm not sure which one is better or not. It's really hard to know that.
Right. I mean, it would be really cool to see a comparison between this and a SOM, for example.
Yes.
And the main motivation behind a comparison like that is basically that in a SOM, you can give it information about all the colors instead of just the 3 colors that you're choosing.
That is
and
true.
So with that excess information, if the performance improves.
Yes, I think
might
so.
Be interesting to say.
Yes.
And the second is, so for the training sample, did you get the redshifts using easy originally? Like when you said that you assign a redshift based on the cell.
No. So for the training sample, the photology we use is actually from the CANDELS photology, the CANDELS median photometric redshift from the CANDELS catalog.
Okay, so is this the V1 photometric redshifts? Like, is this the one based on the Santini mass catalog?
Yes.
Okay.
That one.
Because Dhrita and Kodra was working on an improved version of the photometric redshifts catalog. So I can send that to you if you're interested. Like, we have been putting together a V2 photometric redshifts catalog for all the CANDELS objects.
Oh, that's cool.
And that's based on, like, it has more spectroscopic redshifts and other sources.
That's cool. Because I was trying. So the thing is that the CANDELS, the old CANDELS catalog doesn't have enough spectroscope redshift in those 5 fields, especially in Cosmos field. So I had a bit difficult to find the spectral sample in the CANDELS catalog. Actually, it's really cool. Yeah, I really want to see the updated photometric redshift catalog.
Right. Okay. So let's talk about that offline.
Sure. Yes.
And the last question is a minor one. So can you go back to the place where you were showing the sigma NMAD?
Yes.
So this is just a curiosity, but do you know why the sigma NM80 sort of goes down and jumps back up between redshift 1 and 2?
Oh, here.
Yeah, yeah.
It's really hard to actually track at the improvement at each redshift ranges, but so I think here the big jump at redshift greater than 1 or 1.5 is because maybe so the number of galaxies in each bin is actually different for sure, right? And yes, and also I think at this redshift ranges, the photo G actually estimates it's hard to find like is it really Lyman break galaxies or is it like a Balmer break galaxies at this redshift ranges, right? Because especially we have U band from the ground based, so our U band photometry is not great in CANDELS. So maybe that's another reason we have really like a big bump or large scatter at higher redshift. Yeah. So if we have actually really good U band photometry, it will actually increase the precision and scatters will be increased. Yes. I
see. That's really cool. So maybe data from like UV candles might help for that.
That is also true. Yes, yes, yes. I think U band is really crucial, especially in photo J estimation.
Sounds good. Thank you so much.
All right.
Bomee?
Yes.
I have a very simple question back on that slide. You showed that your definition of delta Z has Z phot in the denominator. I would always think
sorry.
spec.
No, this is my typo. Oh, sorry. I didn't realize that. I'm so sorry. I just realized that. Thank you so much.
Hi, Bomee. I also have a really quick question related to Karthik's second question. So in your color cube, you mentioned that you bin them into bins of 0.2 magnitudes and you would query the best fit SEDs for those galaxies, right? So what best fit SEDs do you use? And if so, like what are the templates that go into that process? I know you're using the CANDELS information.
Yes, I didn't explain in detail about that. So here, I use actually SPS FSPS template. Yes, to find the best fit spectral energy distribution of each galaxy in the training sample. Yes.
Thank you.
Thank you. All right. Okay. Now can we move to the next?
Bomee, it's Cami here.
Hi.
I have a quick comment. You mentioned that you don't have many spec Zs in Cosmos. Have you looked into Legacy? I believe there are about 150 galaxies that are in common between Legacy and CANDELS.
It is true. It is true. So actually, in this paper, this is actually recently published in NIR WL. In this paper, I have like more than 1,000 Cosmos spec Z galaxies plot in CANDELS.
Okay.
Yes, I already used the all legacy surveys.
Okay.
Yes.
Good.
Yes.
Lovely work.
Thank you. All right. So next one is actually very interesting. So next I will introduce our recently accepted HST legacy archive, constraining the masses of galaxy over densities at redshift greater than 1 in CANDELS and Cosmos through weak lensing in the NIR IR. So here, the background images here is E Rosetta looking at a black cluster. So the blue is from the weak gravitational ranging map and the pink is from the X-ray observation for your information. So this is our team, including 12 people from US, Europe, and South Korea. Okay, so how do we start this project? It really starts from Euclid. Euclid is a European Space Agency mission and is scheduled to launch in August 2022. It has 1.2 meter optical near IR space telescope. Euclid-wide survey will cover 15,000 square degrees of the sky and image about 1.5 billion galaxies for weak lensing study. Euclid has one broad optical band, Bs, covering RIG band, and 3 near IR band, YJH band. Optical band has a space quality resolution 0.18 arcsecond, and the depth is about 2.5 magnitude shallower than the HST. Each near IR band has slightly worse spatial resolution 0.3 arcsecond PSF for its half maximum, and sensitivity of 24 magnitude, which is about 1 magnitude shallower than the Euclid optical. So these three near IR bands will be used to measure photometry redshift for weak lensing. So Euclid will measure ellipticity of galaxies only with beads in optical, which has better spatial resolution and the pixel sampling. So this is a diagram showing area of all wide area weak lensing surveys from Cosmos to the future surveys. Until now, there is no weak lensing study using near IR imaging in a blank field, except 4 clusters. So everything from Cosmos to Euclid we use or will use optical images for the weak lensing, except Roman. And Euclid near IR has worse spatial resolution than the Euclid optical. However, it is definitely better than ground-based telescopes having normally 0.6 to 1 arcsecond PSF for its half maximum. Then simply thinking, okay, so Euclid will image billions of galaxies with near IR imaging as well, then why we cannot use those near IR images to measure galaxy ellipticities for weak lensing? There are other benefits to using near IR bands for shape measurement. Here shows 3 HST images at redshift greater than 1.6 in I-band optical and H-band near IR. In optical, galaxies looks clumpy and irregular because at this redshift greater than 1.6, optical wavelengths sample the rest frame UV, which traces patchy star formation. Galaxies in the H-band show smoother light distribution comparing to optical. Okay, here, this is optical and near IR, which because near IR wavelengths sample the rest frame optical light at this redshift, which traces older stellar population. So near IR bands clearly trace the overall galaxy shapes better, especially at redshift greater than 1. So it has a lower shape noise induced from intrinsic ellipticities than in the optical. Moreover, in our 2018 paper, we investigate the value of the near IR imaging for constraining the ellipticity of galaxies using simulated Euclid images. Euclid-like images are constructed from co-added HST data because we don't have a Euclid images yet. So here show comparisons of ellipticities measured from between CANDELS and the Euclid images in 5 redshift bins from 0.5 to 3. In optical, it's a purple color is optical, and this is near IR. So, and here shows some simulated Euclid-like images in optical and the near IR. So you can see some differences visually in different wavelengths. So by doing that, we find that despite the worse spatial resolution and worse spatial sampling and resolution of the near IR bands compared to the optical, the near IR wavelengths provide similar performances in measuring ellipticities of individual galaxies at these redshift ranges. Also, at redshift greater than 1, the near IR selected source density is higher by a factor of 1.4 than in the optical. Therefore, the statistical uncertainty, the y-axis here, in near IR derived ellipticities, blue points here, is about 30% smaller at redshift greater than 1 than in the optical, the orange point here. So this implies that more precise ellipticity measurement, this implies more precise ellipticity measurement at redshift greater than 1 with the near IR despite the worse spatial resolution of near IR bands. Okay. So motivated from this study and or benefits of using near IR bands, we propose to leverage the largest set of archival near infrared images taken by WFIRST HST to derive the first near IR galaxy shear catalog. We will use WFIRST images from CANDELS and the Cosmos Dash. Cosmos Dash here is a HST WFIRST imaging survey of cosmos field in F160 160W filter, which is H band. It covers an area of 0.49 square degrees in the cosmos. It uses drift and shift observing mode, which is called dash technique, which utilize only the gyro for guiding, not the guided star acquisition per pointing like CANDELS. So here I show the dash mosaic and other HST archives, including CANDELS. CANDELS Cosmos is in the middle here, in the Cosmos field. Including CANDELS 5 fields and the Cosmos dash, we will use about 0.74 square degrees in total in this study. Wider Cosmos field observation with the dash technique is approved in cycle 28 as well, so we might be able to extend our analysis up to about 1.8 square degree in total. It's great. So through this project, first, we aim to derive the dark matter distribution in the cosmos and CANDELS fields, including a careful accounting of systematics that affect weak lensing measurement. Even though this project covers a very small area than previous optical weak lensing studies, the depth, spatial resolution, and longer wavelengths of V3 imaging trace components of emission from the galaxy populations that are less affected by shape noise, especially at redshift greater than 1. And our derived weak lensing map can be directly compared with existing optically derived dark matter distribution maps, such as Cosmos weak lensing map, to assess the fidelity of our measurement and provide a new perspective on systematics in the NIR IR data. Second, we will reveal more than 20 galaxy overdensities at redshift greater than 1 in groups and clusters and derive robust dark matter message for them. Especially this, the scale relationship between X-ray luminosity and dark matter halo mass at redshift greater than 1 will be derived from our study would be crucial for eROSITA because eROSITA will detect more than 100 of X-ray clusters at redshift greater than 1 over the entire sky with message greater than 10 to the 14 solar mass. Last, even though the sky area of this project is several orders of magnitude smaller than Euclid and Roman, actually they use the same family of H1R detector of V3. So this study can provide an ideal test bed for understanding the systematics that affect NIR IR weak lensing measurement derived from the real observation. This will be valuable stepping stone before we move on to the larger NIR IR data set from Euclid and Roman. So actually after, so based on this archival project, actually we plan to use Euclid NIR images after the launch of Euclid and every public data will be released. Okay, so before the end of my talk, I would like to let you know my next adventure in South Korea. So end of this year, I will start my new position as a scientist at Korea Astronomy Space Science Institute. So stay tuned my future next adventure and my future studies. Thank you so much for your attention. Thank you.
This was great. Thank you, Bomee.
Any question about our archival project and the photology and other things? No.
Hey, Bomee, this is Yichen.
Hi, Yichen. Hi.
Hey, so nice talk. So very interesting. So for the ellipticity part, I'm just curious. Do you have to know the intrinsic ellipticity to constrain the weak lensing? Because what you got is the observed. It's the, it's one after being lensed.
Yes, yes. So the thing is that actually the reason. So I think I mentioned earlier that the weak lensing is really statistical study. So we actually average or individual observed ellipticities. So by doing that, the intrinsic ellipticity is actually it's not actually going to 0, but it's almost like a neglected because the average of the intrinsic ellipticity is actually about nearly 0 because intrinsic ellipticity is random. It's really random. So we don't need to actually know the intrinsic ellipticity.
I think that depends on the types of galaxies.
But you can imagine that we actually average over a lot of galaxies in a small patch of skies. So in that sky, in the groups or sky regions, there are like all kinds of galaxies, as like a different morphology and everything. So ellipticity actually has like plus minus values, as you might know or not. Actually, I just learned from this project. I didn't know that very well before. So they have like plus minus sign because of the direction and everything. So it's actually when you average out, we consider, actually it's not 100% zero, but we consider that it is like a zero out.
Oh, so it's not just the traditional ellipticity, it's basically ellipticity plus orientation.
Yes.
Okay, and good to know, thanks. Second question is, have you tested whether the depth of survey has any effect on the measurement? Because I can imagine when you go deeper and deeper, you may be able to say, like, run the stellar halos around the galaxies. That could make a ellipticity larger than in shallower survey.
You mean that the ellipticity? So you mean that the high quality images may have like a larger ellipticities because of the quality of the imaging than the shallower? Is it?
Because you may be able to say the faint more extended stellar halos around the galaxies. So I guess my question is, if you have a shallow survey and if you have a deep survey, it would be interesting to see whether the ellipticity measurements are the same in the two surveys for the same galaxies.
I understand what you're saying. So I think it's a good point. So it's actually really interesting. I think it's actually in a point of view of galaxy evolution, people, it is really interesting. I know, but in a point of like a cosmology people, actually that is not interesting. You know what I mean? Because they don't care about the individual shape of galaxies.
Okay.
but I think it's a really good idea, and also it's actually one of the tests we can do in our project, because we are gonna compare the shallow depth images in Cosmos and with the high quality images in our near IR imaging and from the CANDELS and DES in the near IR. I think it's the one science case we can do in our project. Yes, it is true. It's a good. But in the point of cosmology people, the difference between depth of the imaging is that you can get more resolved galaxies. So you have a higher number densities with high quality imaging, and you have a lower number density in the shallower depth images. And if you have if you have a smaller source density in the shallower images, they will maybe increase like beam size of the redshift, something like that, to increase the number of galaxies in each beam size or something like that. So it's like recleansing is actually really, it's really different. That's what I learned from this archival project.
Okay, great. Thank you.
Thank you.
Bomee, I have a related question to what just Yicheng asked. Related to the depth itself, like have you looked into maybe using synthetic data sets, like like Greg Snyder and et al. have produced like mock images, and you can add whatever depth you want to them, and maybe understand like what Yicheng is trying to say, like play with the same data set but with different amounts of just noise added into them that sort of realistically mimics like maybe candles or something, and test what the ellipticity distribution looks like if you looked at the same data set at a shallower depth and see if that induces any systematics in your measurement of weak lensing.
Yes, it's a possible. Actually, in weak lensing, we use intense simulation of images because we need image simulation to validate our our shear measurement. Because we measure the shear from the observation, but actually there is no way we can test and validate your shear measurement. So what we normally did is that we make a simulated images, but we try, so the thing is that this weak lensing and the ellipticity measurement, the PSF and the detector systematics is really important because detector systematics and PSF actually change the shape of the individual galaxies. So to do that, you have to add all detector systematics and the realistic PSF to the simulation. So actually that is really cool. So by doing that, we make a mock, like as you say, the mock images and measure the ellipticities and shear again and compare. And then we got actually the biases of the shear measurement. That is one of the core for map the distribution of the matter. Yes. We normally use GARSIM and our people use the other things. So you can check GARSIM. It's one of the main program simulation for the weak lensing.
Thank you.
I have another question. How do you deal with point sources? At high redshift, galaxies may not be extended, and it's very hard to measure ellipticity for them. And so you are missing some, if we assume that, for example, galaxies in over densities are quiescent galaxies tends to be compact sources, probably point source at high redshift, and you are missing galaxies in overdense halos at high redshift, hypothetically, and then it can bias your shear measurements, or?
I think it is really good point because so the thing is that no one did weak lensing measurement at redshift, right? So Cosmos weak lensing using the optical imaging, the Cosmos weak lensing is until, they say that it's until 1.5 or the DES is like 1.3 or something like that. But normally it is really limited to the redshift is about 1. So it doesn't go up to the higher redshift. So that is actually our challenge. So we have, I think for that, we really need a good PSF for the point source. So we are actually, so one of our main tasks, maybe it's, so this is actually our workflow. It's really complicated. So you don't need to understand everything. It's really complicated. So you can see that actually our one of the main work is about all PSF and the detector systematics. So it's a really intense work. So we are trying to model the PSF as much as you can, because as a function of like position and the color, because as you mentioned, then the quiescent galaxies, PSF as a function of color is really important, and wavelength is also really important in our shape measurement. So it's really kind of our challenging. Yes, it's a really good point. Thank you. Yes.
Are there any other questions? All right. So if not, Bomee, thank you so much